the other section has already had their class. So those of them who belong to the other section but were absent, I may be calling out their names as well. Don't bother, right? So when I call out your name, you just respond. That is sufficient. So just be alert because it is not going to be section wise, as I told you, right? The first is Shobul Mondol. I think he's in the other section. Next, Ashish Shubhomoy Bishwas.
Yes, ma'am.
Right.
Hello, ma'am.
Yes, Shubhomoy, I've marked you. Thank you.
Okay, ma'am.
Sommodip Boshak. Sommodip Shovik Mondol. মৃন্ময় বর্মন, প্রশান্ত গিরি, সৌরভ শীত, হর্ষ কুমার উপাধ্যায়, অমৃতাংশ কুমার, অভিমন্যু কুমার সোনি।
Yes, ma'am. Amritanshu Kumar.
অমৃতাংশু, okay. অভিমন্যু কুমার সোনি.
Yes, ma'am. Present, ma'am.
Abhimanyu, right?
Yes, ma'am.
Okay. Kishan Kumar Singh. Kishan Kumar Singh, not present. Okay. Okay. Orko Chattopadhyay.
Present, ma'am.
Rohit Kundu. Rohit, okay. I've marked you present, Rohit. Anirban Roy.
Present, ma'am.
Okay. Shumanto Pathak.
Present, ma'am.
Okay. Ankesh Kumar. Ankesh Kumar. Pavan Kumar.
Yes, ma'am. Present, ma'am. Pawan Kumar.
Pavan, okay. Shinjan Patro.
Yes, ma'am.
Okay.
Ma'am,
Rishabh Ran.
excuse me, ma'am, there is two Pawan. My roll number is 1147.
47, right. I've marked you.
Thank you, ma'am.
Rishabh, yes. Rishabh Ranjan.
Present, ma'am.
Dash.
Present, ma'am.
Okay. Victor Mondol. Victor Mrinmoy Bormon. Where is Mrinmoy Bormon? Did I call you just now? Mrinmoy, I think, I mean, if you have not responded when I called your name, again, tell me at the end of the class because I'll have to again go back and search. Okay, so Mrinmoy, I have not yet marked you. Keep it in mind. Victor Mondol. Shreya Giri. Shreya?
Present, ma'am. Hello.
Okay. Anish Agarwal. Rahul Agarwal. Rahul. Pooja Datta. Pooja Datta. No? Okay. Next would be, okay, I think he's in the other section, but anyway, Supratik Ghoshal. Priyanshu Ranjan.
Yes, ma'am.
Rahul Talukdar.
Yes, ma'am. Present.
Ankit Abhishek. Ankit
Yes.
Abhishek, yes.
Yes, ma'am.
Okay. Ravi Ranjan.
Yes, ma'am.
Okay. Pavan Kumar Barnwal.
Yes, ma'am.
Okay. Rajesh Kumar.
Yes, ma'am.
Okay. Avinash Kumar. Avinash Kumar.
Yes, ma'am.
Okay. Faizan Ahmed Dar. Faizan Ahmed Dar. Not there. Okay. Okay, Faizan is present, right? Okay, Faizan, I've marked you. Okay. Next would be Yash Singh.
Yes, ma'am. Present.
Okay. Harshit Mathur. Harshit Mathur. Shubhodip Bhattacharya.
Present, ma'am.
Okay. Paras Hela. Paras. Okay, I've marked you, Paras. Shoham Chattopadhyay.
Yes, ma'am.
Shoham, I've marked. Prabuddha Mishra.
Yes, ma'am. Prabhuda. Present, ma'am.
Okay. Saptarshi Mandal.
Present, ma'am.
Okay. Shubhajit De. Shubhrojit De, sorry.
Yes, ma'am. Present.
Okay. Spandan Sen Chaudhary.
Yes, ma'am.
Okay. Kumari Amisha. Kumari Amisha.
Ma'am, she said that she's having some internet trouble, so she's trying to join sometime later.
Anyway, not yet joined. Okay. Koilada Akhil.
Present, ma'am.
Okay. Next would be. Rupoy Tudu.
Present, ma'am.
Pratul Vaidya. Pratul. Okay. Sugata Bishwas.
Yes, ma'am.
Okay. Dipon Burman. Dipon. Jayanto Moi.
Yes, ma'am.
Jayanto. Okay. Aryan Kumar.
Yes, ma'am.
Okay. Ankan Hauladar. Kaushik Mahata.
Yes, ma'am.
Kaushik, right?
Yeah, ma'am.
Okay. Ankun De.
Yes, ma'am.
Okay. Sheikh Mohammed Shakir Huda Ahmed.
Present, ma'am.
Ma'am, well present. Rahul Agarwal.
Who is it? Sorry, I didn't get you. Somebody spoke in the middle.
Rahul Agarwal, present, ma'am.
Oh, you have to wait till the end and then tell me. I cannot do it in a haphazard manner. Just wait. Let me finish through the whole and then. Aman Kumar.
Present, ma'am.
Okay. So that actually completes my list. I would now ask you, okay, anyone from measurements and instrumentation who has not responded?
Ma'am, 1108 Ashish.
1108 Ashish. Anyone
Yes.
else from measure? Okay, I've marked you.
Ma'am,
Anyone
on
else?
33 Dipan Bormon.
Ma'am,
Sorry, one at a
33.
time, one at a time.
Hello.
People keep on entering. 1133.
33 Dipan Bormon.
I'm asking measurements and instrumentation. Anyone else from measurement and instrumentation who has not
Yes, ma'am.
responded? Tell me your roll number or
1165.
name. Name
Saurabh sheet. 65.
1165. Sure of sheet. Okay. Anyone
One
else
on
from
1155.
1155? Mrinmoy, right?
Yes.
Ma'am,
Okay.
1161.
1161. Prashant Giri, is it? Prashant?
Yes, ma'am. Yes, ma'am.
Okay. Anyone else from measurements who who still has not responded? I didn't hear that. Who was it? Who is it? Can anybody understand? You can repeat. I cannot understand who's speaking. Anyone else from measurement and instrumentation who has not responded yet? Somadip Boshak, Shovik Mondol, Harsh Kumar Upadhyay, Kishan Kumar Singh. Okay, Kishan is present. Okay.
Ma'am, Harsh Kumar Upadhyay.
Harsh Kumar Upadhyay, okay. Anyone else from measurements? The last time I'm asking, I mean for now.
I'm Prashant Giri present though.
Ashish Kumar, I've already marked you, don't repeat. Okay, I've told. Ashish, okay. So
Prashant
next, yes,
Prashant Giri.
yes, you also have actually written, no? Written or responded. Prashant, I've marked. Next, okay, now high voltage I've come to. Ankesh Kumar, are you there? Ankesh, Victor Mondol, Rahul Agarwal.
Yes, ma'am.
Okay, Rahul is there. Pooja Datta. No. Okay, so anyone else from high voltage who has appeared later, means logged in later after the attendance was taken. Okay, next would be illumination. Okay, illumination, I think most of them have responded. Supratik Ghoshal, I guess, is not in this section. Okay, so illumination is completed. Power system. Okay, Harshit Mathur, are you there?
Yes, ma'am.
Harshit, okay. Fine. I've marked you. Next is machines. Who is left? Okay, Kumari Amisha, are you there? Kumari, okay. Right, so Amisha, I've marked you present. That completes that. Now coming to control. Who is left out? Pratul Vaidya, not yet there. Deepan Burman,
Yes, ma'am.
okay. Ankan Hawladar is, I guess, not there at all. Else is left over here. Okay, so that completes the list for control. So anybody else now who has either come in just now or would be coming in during the class, I would again ask at the end of the class for those. Okay, so we cannot keep on with this any longer. So anybody else who has been left out, meaning has not been able to respond or has joined after I called your name for the last time, please wait till the end of the class and then let me know that you are there. Okay. So we proceed with the class over here. I will go to the presentation mode and then we'll start the class, right? So just wait, give me a moment. We'll also start the recording and then so though I am recording the class, it is for my records only. Okay, so I'm not going to send the recording unless there's a specific reason to do so, meaning that there's some problem, specific problem. Otherwise, please listen carefully. The recording is not going to be sent. Okay, so anyway, right. So Right, so can you see the whole screen? Whole screen meaning on the right hand side I have a PowerPoint presentation open, and on the left hand side I have a video which is not on, of course, but there are two panes, right? You can see everything. So right now, I mean, we are going to start with the experiment. I will actually be saying certain things and also showing you the slides corresponding to that. And then as we require, I'll be showing you a bit of video recording, a clipping, not the whole experiment. It's not possible to do that, but the basic connections, etc., will be shown via the video, right? So here we are about to study this experiment, that is study of speed control of DC servo, which is experiment number 8. It was supposed to be performed in the control systems lab, as you are aware, right? So the objective of the experiment first, right? So to configure the closed loop speed control system using standard servo system blocks and to study its stiffness against load torque. So that is the objective. As per, I mean, as far as this objective is concerned, it is taken from the instruction sheet. So I am sure all of you have got the soft copy of the instruction sheet, and we'll be following the same instruction sheet. The objective is there and the title as well, as is the block diagram that you're going to see over here. Now I'll just give an overview of the block diagram, and then I'll show you the components, each of and the function and the close view of each of those components is what we are going to deal with. Then the connections, how those components are going to be connected together with the help of the video we'll be seeing. And then finally, I'll be giving you a sort of experimental a sheet where some experimental data has been handwritten. It has been noted by some student earlier in some earlier year that will be shown to you. After the experiment is over, either today in the evening if I find time, or at least by tomorrow, I'll be sending you the only the sheet with the experimental data via email to your common mail ID, right? You would be requiring to complete the report. What you are supposed to do in the report is given in your instruction sheet as well. So based on the data that you find on that sheet, you would have to complete the report and then make it into a PDF and send an email to me, to the email from where this link for this class has been generated or sent, right? So that's smita.sabighosh@jadavpuruniversity.in. You need not note it down, you will find it. It's the mail from which the link had been sent. So that, you would have to submit your report, say, within next Friday would be what, 1st October, or at the most 1st, 2nd, 3rd, 4th October. Okay, that would be the next Monday. So that deadline I'll be repeating at the end of this class when we finish this class. So on or before the deadline, you would have to send a PDF version of your report to my mail ID, right? So now coming back to the block diagram, you find over here there are several components which are shown in the block representation. The first of which is a potentiometer, you can see over here. Then the summing amplifier, right? So in the summing amplifier, you find one input coming directly from the reference input port. The other input is actually coming from the feedback path, right? Then the amplifier output goes to a PID controller that is connected to a preamplifier, and that the output of the preamplifier is connected to the servo amplifier, from which an armature controlled DC servo motor is excited, right? You also find you can see the field connection over here, but it is in the armature controlled mode, this servo motor. And then the shaft of this armature controlled DC servo motor is coupled mechanically to the tacho generator. And then you find here, this is an arrangement to give, it is known as the brake, BRAKE, and it acts as the load, right? So, you can increase or decrease the position over here. We'll see how that is done. The video, you will be able to make out a bit regarding how mechanically the position can be changed over here. Anyway, by changing the torque, by changing the load torque, you would be, having to take different readings. So that completes the blocks, just, sort of the names of the blocks that you find over here. Now, as far as these are concerned, the summing amplifier, of course, performs the task of amplification, as well as it sums whatever is at its input. The preamplifier is another stage of amplification. I mean, it is going to perform the task of amplification. In our lab setup that we have at Jadavpur University Control Lab, preamplifier is not used. But if we had used it, it would just be an extra stage of amplification only, right? Then we have the servo amplifier. That also is another stage of amplification, right? So the servo amplifier actually supplies the DC servo motor in the armature controlled mode. So now let's proceed. This is a photograph of the setup that is there in the control systems lab. We'll see each of these components separately. Now, I mean, this, as I told you, is means in the block diagram you find that over here, this one is going to act as the load, right? It's going to provide the brake, and the other components we are going to have a closer look at just now. So first of all, the power supply unit. Now, this is the setup that you saw in the previous slide. Over here, this unit over here has been shown separately. You can see that, right? So this is how it looks like. Now, in this unit, what you find is, first of all, the name of the manufacturer is written over here. It's Feedback UK. The name is Feedback, name of the company. And the name of the block over here, PS and 150E, right? Because it's a power supply unit, I guess they have used such a code. So it's a power supply, it's written over here, right? And then you can see that there's an indicator over there. Now, the rest of the things, as you can see, there are several terminals. You see plus 15 volt, 0 volt, and minus 15 volt. That is a set over there. You also find that there are several other terminals from which you could be tapping the supply, right? Say, for example, over here again, you find plus 15, 0, and minus 15. So, I mean, you can actually power up different components, whichever of the components required to be powered up separately can be powered up from this power supply unit that you see over here. Next, in the setup, that is this one, you find this particular component over here, which is shown in an amplified form. Actually, there are two of such components if you have a look at the setup. One of which is the input potentiometer and the other is the output potentiometer. So basically over here, this is sort of a representation of what you would be finding at the front of the panel. This is what it would look like, right? So the name you find over here, name of the component, I mean, right? Input potentiometer, so IP, and then the port, whatever they have given, 158. This is the input potentiometer for which the circuit diagram, whatever is inside, is shown over here. So you can see basically here there is a resistance, right? The two terminals being 1 and 2, right? They are shown over here in the left hand side of this middle diagram. 1 and 2 terminals are shown, and then you find that the pointer is actually connected both to this side or that side, which actually ends up in terminal number 3. So the output would be taken in this diagram. This is terminal number 3. The output would be tapped from there, output of this input potentiometer. So as far as this input potentiometer is concerned, you would have to put in a supply over here on this side and then get the output from the other side, this side, right? Similarly, the output potentiometer also has 2 terminals which can be powered up and you can tap out the output from this side. The circuit diagram corresponding to that is shown over here, more or less. I mean, what represents what you would be expecting if you open the top panel. You would be expecting something like this, a resistance, and then the pointer would be there. So, next we come to what we call the attenuator unit. So, this unit is the attenuator unit that you find on the tabletop in the experimental setup, I mean, and this is what it would look like, right? So in the attenuator unit, you have knobs or dials like this one, right? So in the dial, basically, there is an option of changing the dial position, and accordingly, you would be giving the, you would be applying the input accordingly, right? So the attenuator unit is going to control how much of, okay, let me show you this one. This side, actually, you can see the pot is shown. Pot means potentiometer is shown, right? So basically now this 1 and 3 would be powered up, and from 2 we are tapping the output. That is as far as the potentiometer is concerned. We showed on the last slide, the previous slide. Now how much of output you are going to get is what is controlled by changing the position of the dial over here, both for this unit as well as the other unit. So there are two such attenuators consisting of the attenuator unit. One is controlling the input pot output, and the other is controlling the output pot output, right? So depending on the dial position, you would be able to change the voltage which is being applied at the input side if you change the position over here, as well as what is going to come in the feedback. We are going to see that later on by changing this attenuator, this attenuator, changing the position of this dial. Next we see this unit over here, which is magnified. The front panel would look like this. You can see that this is the operational amplifier unit. Op-amp unit name is given over here, and this is what it would look like. A sort of connection diagram is shown over here. Circuit diagram is shown over here. Mostly, I mean, how the connections are made and all that. At least it's shown as the resistance and capacitance and all that, right? So in the op-amp unit, you find, first of all, there is a provision for powering up the op-amp unit. So this, these three terminals at the top are the terminals where you would be connecting the power supply, so that the rest of the, the rest of the unit works, right? You find 1, 2, and 3. There are 3 input terminals where you can apply the input, and one single output terminal, but as far as terminals are concerned, there is a provision of taking out 2 tappings from there, but it's the same. You can see it's basically whether you take it from here or there, it's the same thing. So basically, you can see that over here too. So it's the same connection, 666, it's written, the same number is written several times. You can either take it from here or there, it doesn't make any difference. Whereas, as far as the input terminals are concerned, 1, 2, and 3 are 3 separate input terminals, right? So that is as far as the op-amp unit is concerned. Next, we have the PID unit. I'll be speaking more about the details of the PID unit a bit later on. We will be looking at it in details, but not just now. Okay, so next we have the pre-amplifier unit. So that is also present in your experimental setup. That is this one. Okay, as I told you, for our experiment, we would not be requiring to connect it, but had we required it, you can just have a look at it. So as I told you, it's just an amplifier unit. So another stage of amplification, you can say. So this is what the front panel would be looking like, and you can see that there is a provision of powering it up from the power supply unit. The input terminals can be applied over there, and the output can be tapped out from the other side. So on the right hand side diagram, this one also, you can see the same thing. That is, these are the signal inputs, and the output can be taken from there. The power supply can be connected there. Next, we have the servo amplifier unit. Now, as far as the servo amplifier unit is concerned, this is this red, not square exactly, but the red, line over here is actually encircling the servo amplifier unit, this one, right? Now, this servo amplifier unit is internally connected to what is on the right side, that is this one, which is the power supply unit. So there is internal connection between the servo amplifier unit and the power supply unit, such that the servo amplifier unit for our experimental setup would not be requiring external power supply to be connected. It is internally connected and powered up, right? So in the servo amplifier, you find that there are 3 terminals denoted as plus 15 volt, 0 volts, and minus 15 volts. From here, you can try to power up some other unit, meaning that this will be acting as a source of power for some other unit if you so wish. If not, you can just keep it, disconnected, just like, as if you do not require any powering up of any block by, from some extra terminal. In that case, you need not make any connections over here as such. As far as the servo amplifier unit itself is concerned, it's already powered up. It's connected internally to the power supply unit. So only if you require this as a source of power, you can use these terminals to power up some other unit. I hope I've been able to convey what I mean over here. This is specific to the setup, this feedback system, DC servo setup that we have in our lab, right? So the rest of the things, of course, you can see the connections are there. Inputs are these, okay, and this is how it looks. Next, we have it is going to serve the purpose of amplification again, right? Next, we have 3 units, which are the motor unit, the tacho unit, and the load unit. So of those, now in the experimental setup, that is this one, the photograph, you find this unit within the red encircling. This is the DC motor, right? So in the DC motor, you find basically there are only 2 terminals across which you would be able to connect your whatever is coming. If you want to sort of give some signal over there, you would be having to connect across these 2 terminals of the motor, right? Now, this blue encirclement over here actually is showing what we call the tacho unit, right? So tacho generator unit is this one shown over here, right? So here again, you have, different terminals are shown, but they are, as you can see, this is the tacho itself. So if you tap it from here or from there or from, on the other side from here or there, would be amounting to the same thing. So basically, this is the tacho generator unit. Now, next, we have a look at the load unit, that is within this green encirclement over here, this one, which actually acts as a load unit. So there is a sort of arrangement by means of which this this unit can be rotated about an axis such that we'll see the video. You will understand that this can increase or decrease the load by changing the setting over here, and accordingly the speed of the motor will be increasing or decreasing. It will be changing according to the value of the load that you set over here by using this block, right? So this is the load unit. So together you can see these are the 3 units, and you can also see that the motor shaft is directly mechanically coupled with your tacho shaft. So this is the shaft that I'm speaking of, and when applying the load, this is a disc actually. It's not. This is, you can say, the top view of that. Okay, so this is a disc, and by sort of changing the position of this braking unit, the brake can be applied on the braking torque can be applied on the shaft of the motor tacho unit, right? So basically, it's going to be changing the load. We'll actually see the video. When we see the video, you will understand how exactly the changing is done. Or rather your batch, you didn't have the lab in the lab last year as well, right? So maybe when you visited the control lab in the second year, you may have had a look at this setup, so I'm sure you've forgotten. But anyway, I'll be showing you the video where sort of you would be able to understand at least vaguely how physically how the load is being changed. You should be able to sort of get an idea regarding how it's being done. Anyway, So now we come to the instruction sheet. This is nothing written by me. It's the same instruction sheet that you have in your position. So the procedure is given over here. I'm not reading it out from this. And then, of course, there is a table where you have the tabulation as well as some relations which are given over here, from which you would have to do some of the calculations, and then the, proceeding with the steps of the procedure, you have this, and then finally the report. So this sheet would be important. After I finish this class, you would have to do not the first one, tabulation of the result. Actually, I'll give you the table of the result, and the appropriate diagram would mean the block diagram you have to redraw. But apart from that, now drawing the signal flow graph and then calculating and comparing, then finally drawing the plot, these you would have to complete according to what is written over here. So that's why I just wanted to point it out. You can read it later on. So now I will sort of try to outline the way the connections are to be done. Of course, it is going to follow the block diagram, which is already supplied in your instruction sheet. But of course, as far as the lab equipment is concerned, you can have a look at how it is being done. So I will be playing the video, but I will be stopping the video here and now and then, and will be speaking to you. Also, have a look at the right side panel where I have actually tried to write down most of what I would be saying. So I'll just bring it to this one. Okay, so narration 1. So I'm starting the video, but I will be stopping it and then speaking to you. And you could also have a look at this slide on the right hand side, which is going to correspond to whatever I'm showing and speaking. So starting now. Okay, so this is the setup. You can see it from one side. And okay, so the units you can just see. So first, basically, what is going to be done is the powering up is going to be done, and powering up of the op-amp unit. So you can see in the narration slide, this is the op-amp unit, which one I'll of course show you. Yes, so this is the op-amp unit. You can see the person is actually pointing to that, right? So this is the op-amp unit. Okay. So now is pointing to the points where the input signals may be applied, and it can add up to 3 signals. You have seen 1, 2, and 3 terminals are there to which you can apply the input signal, right? So it can add up to 3 signals. Okay. So now, okay, so now what is being done is you can see the right hand side panel over here. This one panel means I'm referring to the PowerPoint slide. You can see the first connection is that is going to be done is shown over here in the red line. Red line means the output of the input port, that is this terminal 3 of the input port, is going to be connected to one terminal, that is the input terminal of the op-amp unit. So this is the connection shown over here, which is being done in the video right now, which will be done in the video. Okay, so you're right. So you see the output of the input potentiometer is being connected rather to the input side of the op-amp unit, right? So the corresponding slide, as I told you, I'm just repeating in case you've missed, that is shown over here, and the connection is being done in the video, right? So that is taken care of, right? So next, I'll go to the next slide where we will be continuing with the rest of the experiment. So right. So now the person is pointing towards the input port unit, this one, right? So the input potentiometer unit actually has to be powered up, because I mean you've tapped the output and put it into the input of the op amp, but the input side has to be powered up, otherwise you are not going to get anything at the output, obviously, right? So he's going to power up the input port. So corresponding to that, you can see this slide, the right hand side panel. The slide is showing how the input port is going to be powered up. Now, if you recollect, I had mentioned while showing you the units that the servo amplifier unit also has a provision of acting as a source of power. So basically the connection that is going to be done is shown over here. You can see the input side of the potentiometer, that is terminal 1 has been connected to plus 15 volt and terminal 2 has been connected to 0 volt. So that is the connection that you are going to see next in the video. Let us see the video now. Yes, so this one is being connected to the plus 15 volt. So that is terminal 1, as you see over here. Okay, so the other terminal, that is this terminal, terminal 2, is connected to the 0 volts. It's being grounded. So that would give you a range at the input side of 0 to plus 15 volts. So that's a range of 15 volts that you would be getting, right? If, say, for example, I would have connected this terminal 2 of the input port to the minus 15 volt, then the range that I would be having at the input side would have been from plus 15 volt to minus 15 volt, a range of 30 volts, but with a 0 volt in the middle. But that is not what is being done over here. We are going for the 0 to plus 15 volt range, right? So the other terminal is now going to be grounded. You say, you see, this terminal is going to be connected to the 0 volt of the, yes. So you see it is being connected to the 0 volt. So it's exactly the same that thing that is being done. You can see that in the slide as well as in the experiment that is in the video, right? So okay, that completes this narration 2 slide, right? Next we proceed again. So proceeding with the video. Okay, so now over here, first I'll say what's going to be done by showing you the slide. Here next, what is going to be done is the output of the op amp unit is going to be connected to the input of the servo amplifier unit. So basically that is what is going to be done, because in your block diagram you will be seeing that the op amp unit is connected to the PID controller unit, which is connected to the preamplifier unit, and then that is connected to the servo amplifier unit. If you follow the block diagram, I hope you know what I mean. But as I told you, preamplifier we are not using. Now, as far as the PID controller unit is concerned, we will be making the connection later on. But right now we are, choosing to make the connections for the forward path without the PID controller. So that actually has made us connect the op amp output to the servo amplifier directly instead of via the PID controller unit. If you want to connect the if you want to put in the PID controller unit, this connection you would have to disconnect, then put the output of the op amp to the PID controller unit, and then the output of the PID controller unit to the servo amplifier. That would have to be done. But right now, just for the sake of simplicity, so that you understand what exactly is to be done, and in a simplified manner, we are showing that the op amp output is directly connected to the servo amplifier unit. PID controller is not connected right now. So you would be seeing that in the video right now. Let us see. That is the output that is pointing to now. Output of the op amp is connected to the servo amplifier unit. So that actually, if you have noticed, is this connection, the red connector that I've shown over here in my slide. That connection has just been made. This probe over here is what has been used, right? So next, I'll proceed with my slide first. Okay. So next, what has to be done is that the op amp unit does not have any source of power as of now, meaning that the you can see the op amp unit, we've connected the input side and the output side, but it has not been powered up. So that has to be done next, right? So for that now, this is the op amp unit as you must have recognized by now. And this is the power supply unit. So basically the terminals plus 15 volt, 0 volt and minus 15 volt would have to be connected to the respective terminals of the power supply unit, meaning the plus 15 to the plus 15, 0 volt to the 0 volt and minus 15 to the minus 15 volts, right? So that is what is being done next, will be done next. Let us see the video for that. The powering up will be done. Yes, so he's connecting the plus 15 volt to the plus 15 volt of the power supply unit. So as I told you, this is the power supply unit. So that has been connected. Minus 15 volt is connected to the minus 15 volt and 0 volt will be connected to the 0 volt over there, right? So that actually completes the connection that you see on the narration slide, meaning the slide, the PowerPoint slide that I'm showing on the right hand side pane, right? So that actually, after these three probes have been connected, the op amp unit has been powered up, right? Next, okay, so let us proceed with the video. So he's just tracing the input path. So basically, the input port has now been connected to the op amp unit, and the op amp unit has been connected to the servo amplifier unit. Now, as far as the servo amplifier unit is connected, you see, I've written on the slide, the servo amplifier is internally connected to the motor tacho unit, right? So you need not make any external connection between the servo amplifier unit and the motor tacho unit, right? So that is internally connected, since it is internally connected. And of course, as far as the motor and the tacho are concerned, what is the, I mean, how is the connection done between the motor and the tacho? Naturally, the connection is actually via the, because this is a motor, right? So what is the output of the motor? Basically, the rotation of the shaft, right? So there is a mechanical coupling between the motor and the tacho unit, which implies that again there, I mean, would not be any electrical connection that you would require to make between the motor unit and the tacho unit. So basically, I mean, to sum it up, we've connected the output of the input potentiometer to the op amp unit, and then the output of the op amp unit to the servo amplifier unit, which now is already connected internally to the motor unit, and the motor unit is coupled to the tacho unit via the mechanical coupling. So as far as these connections are concerned, this portion is taken care of. So let us now proceed again with the narration slide. Okay. So now, I mean, the forward path has been connected. A multimeter will be used, and you will see that it will be used to measure the tacho generator voltage. So let us proceed with the video. Okay, so this is a multimeter which is going to be used. So the tacho generator voltage will be measured. So tacho generator voltage means, I've shown you a close-up of the tacho generator unit. There is a circular, I mean, symbol over here, and two terminals are shown. So basically, connection has to be made, the connection of the multimeter to the two ends of this tacho generator has to be done such that the tacho generator will be, voltage will be measured by the multimeter. The only thing is that one end will be actually grounded as well. So you can see one end is to be connected to the terminal of the multimeter. The other end is connected to the ground of the multimeter and also to the ground of the power supply. So that the multimeter will be able to measure the tacho generator voltage. So let us see the connection being done now in the video. This is one terminal which is connected to the terminal of the multimeter. Okay. The other terminal is actually going to be grounded, meaning connected to the, okay, so this terminal is being connected to the ground of the your multimeter, and it is also going to be grounded separately. So this is being connected to directly to the ground of the power supply. So in the power supply unit, here on this side you have a 0 volt, which is actually a grounding. So basically, I mean, one end, that is this end, is also being grounded separately so that we get the tacho generator voltage directly. Okay. From the multimeter reading. Okay. So the connection has connection, meaning the forward path, that is the open loop configuration. Actually, the connection is completed. Of course, we have not as yet used the PID controller block that I've already told you, but just to see the basics, we will now see that the power is going to be switched on and certain things are going to be checked over here. So let us see that. So switch on, okay, switch has been switched on. Okay, so this is the load unit that he is now handling, right? So it's also known as the braking unit, BRAKING, braking unit. By changing the position over here, actually there is a pointer somewhere over here, and I mean, depending on whether he is putting it like he has put now, or whether he is taking it closer to this disc. As I told you, there was a disc, the top view of which you saw in that diagram. This is the disc in question, this one. You can see only a portion of it, but now over here, basically this unit is going to be either closed in on this disc or taken far away, and there is a sort of, I mean, braking arrangement by changing the eddy current that is flowing. So basically, that is the way mechanism by which it is done. Nevertheless, I mean, what we would have to do as far as the experiment is concerned is that by changing this position, we would have to take readings. So let us see. Okay. So this particular, I mean, position, you can see that the disc is, I mean, the whole of this unit is outside of the disc, right? So this is probably corresponding to the no load condition, I think. Let me see. So the brake position can be adjusted. You can see that in my PowerPoint slides on the right side, right? Zero brake position means there is no load, and you see that the motor is rotating. We'll see the rotation, but before that, you would also have to note that as the load is increased, the speed will be reduced. And of course, you can read that from the tacho generator voltage. So that is what is going to be shown in the video over here. Let us see successively. Okay, so you can see the rotation. It's rotating very fast. Okay, so now increase in the load has made the shaft rotation much slower, right? So it means that so decrease in the load has increased the rotation, meaning the speed of rotation. Increase in the load will be decreasing the speed of rotation, and correspondingly the tacho generator voltage can also be checked, right? Right. So here again, some load has been applied. So actually, I'm saying some load, but basically, as far as the load is concerned, there are, I mean, sort of markings over here. You can apply markings. I mean, loads corresponding to markings of say 2, 4, 6, 8, 10, which you will be finding in your, I mean, finding in the experimental data sheet that I send you. You will see that over there the notings would have to be taken by putting the load at position number, brake position, we call it, brake position 2, brake position 4, 6, 8, 10. So there are, I mean, actually, I mean, 5 such possibilities, 2, 4, 6, 8, 10, apart from the 0 value, of course, corresponding to which the readings have to be taken. So 0 position would indicate no load, 10 position would indicate full load, and the others are all intermediate. So let us proceed with the video. Right. So now what he's trying trying to do is that he is now over here on this side, he is trying to change the attenuator position so that the input pot voltage, or rather the voltage which is applied by the input potentiometer is changing, right? So changing means, first of all, he is going to decrease the voltage to a very low value and show you that the motor will almost stop, or in fact actually stop. Let us see the next. Yes. So, okay, over here on my slide, you can see if the input side voltage is made almost zero, the motor almost stops. So that is what he will be showing next. So he's just, changing the attenuator. He has now made I'll just put it back by 10 seconds. Let's see. So, okay. So here now the motor is rotating. He's going to make the input voltage equal to 0, and you will see that the motor will almost stop for that. Okay, so let us see that. Okay, so now it's rotating, but okay, now it's made 0, almost 0. So you find that the corresponding to the 0 input, there will be, the motor will stop, and gradually he is increasing. Then you see that the speed will be increasing gradually. So by changing the input voltage, you would be able to actually change the speed of the motor, right? So the speed of the motor is controlled by changing the input pot, right? Okay, showing that again once more. Right, so now something to be noted, that is, by changing the input pot, we can change the increase or decrease the voltage which is being applied, and correspondingly there will be a speed change which is going to be noted. You can note the values, of course, if you are performing the experiment directly. That is understood. Now, one thing to be kept in mind is that we have used an op amp over here, and this op amp is actually an inverting op amp, or rather we are going to check whether it is inverting, right? So as far as the motor unit is concerned, a positive voltage has to be applied to the motor unit. Now what this person will be doing is that he will be checking whether the output of the op amp has a positive voltage or not. If the voltages seem to be negative on the output side of the op amp, then he is simply going to reverse the input side voltage so that he gets a positive voltage at the output of the op amp, so that a positive voltage is actually applied to the servo amplifier and hence the motor, right? So that is what is going to be checked next. Let us see. Okay, let us just have a look at this, and the polarity will be checked. Okay, so next what is being, there was some frames were skipped over there. You find that a connection has been made over here, this red probe that you see. There's another multimeter which has been used over here, and the output of the op amp unit, the polarity of the output voltage of the op amp unit is going to be checked, right? So if the polarity, as I told you just now, just before this, if the polarity is seen to be negative, then we need to reverse the input terminal voltage, because if a positive voltage is applied on this side, it's going to be reversed or inverted, and you are going to get a negative voltage at the output of the op amp. But we want to apply a positive voltage to the motor side. So that would imply that if we now, by means of this multimeter, if we find that the voltage is negative, we are simply going to make appropriate changes such that the output of the op amp has a positive voltage, right? So let us see that. Okay, so what he is doing is, I'll just, so now, I mean, there are two terminals of the multimeter. One is the ground, which has been grounded. Yes, just connected it to the ground somewhere. I mean, over here there is a 0 volts connection. So that has been grounded. One end of the multimeter has been grounded, while the other end of the multimeter is connected, other terminal, I mean, of the multimeter is connected to the output of the op amp, so that he wants to check the polarity of the output of the op amp. This video will end, but I have a second video, part of it, continuation of this rather. So I will just be going to that video once this finishes. Okay, so you can, okay, vaguely see that there's a negative sign over there, but I'll show you, there's a reflection. Achha. Now this. Okay, so now this is the video 2, second video that we have. Second video means it's a continuation of the first one. The same thing being continued by, I mean, I have two files separate for the first part and the second part, that's why. So now we'll be seeing a continuation, meaning that the output of the op amp will now be, polarity of the output of the op amp will be checked. Let us see that. Achha. Is it visible? So you can see that the output of the op amp now is connected to the this multimeter, which is showing you a plus, showing you a minus 10.6 something volts, right? So this, I think I have to do the next slide. So, okay, so narration 11, you can see that slide. On measurement, we find that the voltage of the output of the op amp is around minus 10.6 volts. So that is the reading you see over there. So that means that the output of the op amp has a negative polarity, negative voltage, right? So that we would have to now change the input side voltage appropriately, such that input side means the input of the op amp should be negative, so that the output of the op amp is a positive one, and that positive voltage will be applied to the motor. That is what I mean, right? So that is what is going to be done. So this is a negative voltage at the output side of the op amp. So now how can we achieve a negative voltage on the input side such that it is inverted to get a positive voltage at the output side? Simple thing is that the input of the pot was connected, if you recollect, from within a range of 0 to plus 15 volts. So instead of that, if we make the input side go from 0 to minus 15 volts, that would imply that a negative voltage will be applied to the input of the op amp, that when inverted will give you a positive voltage at the output side. So that is exactly what is going to be shown over here next. Okay, so he's showing that the input side of the op amp now, I mean, till now, has a positive voltage, whereas the output side we saw was minus something. Okay, so that is being verified and shown to you that it is an inverting op amp. Okay, so negative on the output side and positive on the input side. So now he's stopped the, I mean, switched off the power supply unit, and then he's going to, okay. So he is now going to, this is not the end. Okay, so this terminal now, instead of being connected to the plus 15 volt, has been connected to the minus 15 volt. The other end was already connected to 0. So instead of a range of 0 to plus 15 volt, now a range of 0 to minus 15 volt is what is being applied to the input side of the op amp, right? Because remember that this your input pot output, that is pointer end, had been connected to the input side of the op amp. So that is the minus value. That's going to be checked and shown. Yes, so now you find that there is a positive voltage at the output side. He's also going to check that. No, okay, it's not checked. But anyway, it's implying that in the input side, since you've put a negative voltage, the output side has become a positive voltage, and now we are satisfied with it, meaning that this is the voltage which is going to be applied to the motor. Okay. So now what is going to be done is that the voltage setting, now the polarity has been taken care of. So basically, okay, VI has to be set to 1 volt by adjusting the pot. Okay, so that is what he's doing right now, just to start the experiment. Okay, so he's going to make it 1 volt by changing the attenuator unit. You can see that being done now, around 1 volt. Okay. Now the break position. Yes. So now this is the break position, which is, I mean, being changed. If you put it at 10, as I told you, if the marking is 10, that would be the full load condition. So basically, that is what we will see over here. You will also note visually that the rotation over here, the speed of rotation has decreased because the load has increased, right? So that you can see. Okay, the motor, which you can see the speed of rotation is much, much lesser compared to what we had earlier. Okay, so again over here, basically the tacho voltage is showing as negative because the connection over here was just reversed. So by putting the ground end not to this end but to the other end, the tacho voltage, you just, I mean, switched these two terminals. That's why I'm saying you could have actually from the beginning actually done it this way. So when you are performing an experiment, sometimes what happens is, I mean, if you want a specific range, you want the tacho voltage to be properly noted as a positive voltage. So proper polarity for this noting has to be made. That is what we have just done, so that you get a positive voltage at the tacho end. Right. So this is as far as the video is concerned. Now I go back to the slide only. So I've stopped the video at this and go back to the slide, the PowerPoint slide that I'm showing. So the procedure is, I mean, written over here. I've put it within the red block like this over here. So you have to note the armature current at which the motor starts rotating. Armature current can be noted from this multimeter over here, and the tacho voltage can be noted from this one, whereas the op-amp or input side voltage can be noted from this multimeter over here. So now, of course, I mean, just the you have to get the table, and then basically get the table means you have to construct the table and over there fill in the values by taking the notings. You find over here there is a column for the break position as well. So you would see when I show you the experimental data that keeping the break position at 2, 4, 6, 8, 10, we note the corresponding values over here. We fill in this over here in this table. Okay, so this is the procedure as per your instruction sheet. Now showing till now whatever we have done, we have actually done in the open loop, right? Open loop means only the forward path we have considered. Also, we have not till so far considered the PID control unit, as I told you, right? So if we have to take the closed loop reading, first of all, if we want to take the reading in the closed loop, what we have to do is we have to connect the tacho generator to the other, I mean, you had the other terminal of the op-amp, right? The op-amp means the summing amplifier. So summing amplifier we showed had three possible input signals can be put into that input side. So one we have already used up for the previous open loop case. Now the second terminal, in the second terminal, you can put in the feedback, you can directly connect, and that will make your system run in the closed loop. The only thing that we have not considered so far, as I was saying, of course, preamp we have not connected. As I said, we are not going to connect for this experiment over here at all. But the PID controller you would have to connect and accordingly take the readings by changing for different values of the controller, meaning first of all the proportional controller with a particular setting, I guess it's 0.2, then by putting a value of proportional controller gain equal to 0.6, and then for the PI controller, whatever be the values, basically the PID control unit has to be used and accordingly you have to take the readings. So next we focus on the PID unit, right? So now as far as the PID unit is concerned, you can see the front panel of the PID control unit, right, where there is a provision of putting the power supply. So you find the three terminals over there, plus 15 volts, 0 volts and minus 15 volts. So these have to be powered up either from your power supply unit or from the servo amplifier unit, which actually is acting as the power supply unit again. So basically what has to be done is that the PID control unit has to be powered up from a power supply source, right? Plus 15 volt has to be connected, 0 volt has to be connected to 0 volt, and minus 15 volt has to be connected to the minus 15 volt, right? That's the first job that we have to do as far as the PID control unit is concerned. Okay, so next we turn our attention to several switches that are visible in the PID control unit, right? So, okay, let me do something. I'm not going to use the video anymore, so I'll actually, it's okay, better not to change anything. Okay, so here now you can see it's visible. There are three red arrows that you see and three blue arrows that you see. First of all, we'll be speaking about the red arrows, right? So you find that these red arrows, wherever they are put, this corresponds to one switch over here. This switch can be put either in the in position or in the out position. Similarly, this switch can be put in the in or out, and this one as well, right? So these three switches, which are pointed to by red arrows, are actually used to include or exclude a particular control action. For example, if I switch this switch to the in position, you see if I trace it, this is connected directly to the P controller, that is the proportional controller, right? So this switch, this one, is connected to the proportional controller. If this is in position, proportional controller will be used. If it is in out position, P controller will not be used, right? Similarly, this switch over here, the top one with the red arrow, it's connected to the integral controller unit you find, right? So basically, if this is in position, it means that the integral controller is being used, and if it is in out position, you see that the integral controller is not used. You would have noted that, I mean, two ends are connected, one to the P and the other I. When you have studied, if you have studied, that is controllers, P, I and D controllers, you would have noted that standalone integral controllers or standalone derivative controllers are almost never used. So it is used in the PI mode or PD mode or PID mode, or only purely proportional controller mode, but not only integral controller will never have that possibility, or only derivative controller never have that possibility for reasons which you must have studied. So anyway, so that this switch basically indicates whether my integral controller is in or out, meaning included or excluded. Similarly, this switch over here indicates whether my derivative controller, that's this unit, is in or out, meaning included or excluded, right? Apart from that, we find three other switches over here pointed to by blue arrows. These are the multipliers, which is written over here, and are used to select the controller gain. So controller gain means what? When I multiply by 1, I mean that if, say, for example, 0.1, 0.2, 0.3, 0.1, 0.2, 0.3, 0.4, etc. You see the markings on this side. So if I have put the multiplier setting at 1, it means that 0.3, say, that's a reading, that's where the pointer points to. It's going to be giving me a reading of Ki, or not Ki, Ti is equal to 0.3 into 1. On the other hand, if I set the multiplier to 10 and the pointer is still at 0.3 reading, then the value of the Ti is equal to 0.3 into 10. right? So the multiplier is simply going to give me the value of the integral time, that is Ti. Similarly, for the derivative controller, Td, whatever setting I have over here, multiplied by what gain I have chosen over here. So into 1 it could be into 10, and that would give me the reading that I have chosen. Similarly, for your proportional controller, you find that there is a multiplier switch corresponding to that, right? So that completes the switches that are present in the PID controller unit. Now we will go to how we can use the control actions. Okay, of course, we have to make the appropriate settings by changing the switch positions. But apart from that as well, we have to apply the input, right? So when the P control or PI control is used, the error should be put to this point that is known as the input error. Why am I saying error? You would recollect that in the block diagram, basically, the output of the summing amplifier is what? It is the error, isn't it? So basically, and the output of the summing amplifier is what is connected to the input of the PID controller. So basically, this signal over here is going to be the error signal. That's why this nomenclature over here, it's already called input error. So if you are using this controller in the proportional controller mode, you connect the signal from your amplifier, that is summing amplifier, directly to this point. If you are using in the PI control mode as well, you connect this to this point, that is input error. And if you are using in the proportional controller mode, what else would you have to do? You would have to make the switch, this one, that is the proportional controller switch in the in position, integral controller switch in the out position if you want a proportional controller, right? On the other hand, if you want a PI controller, this connection is still going to remain the same, whereas both your P controller switch as well as the I controller switch, both are going to be in the in position if you want a PI controller. So basically, that is what has to be done for P or PI control. However, for derivative control, something else has to be done, right? So that's corresponding to the second point that I put over here. So if a derivative controller is included, an additional connection has to be done externally. So this red curve that you see, connecting this terminal point, which is written as input error, and this point, they have to be connected externally by using a probe. That has been shown over here. And then if you are using it in the PD controller mode, then your P controller will be in the in position, D controller will be in the in position, whereas I controller will be in the out position. Whereas if you are using in the PID mode, all the three switches will be in the in position. Okay, corresponding to P, I, and D, all those switches will be in the in position while making this connection as well. So this connection from the input error point to this input of the derivative controller unit, that is this one, this has to be done, and additionally the switches have to be appropriately set so that you get the PID controller mode working. Okay, so that is, I mean, as far as the PID controller unit is concerned. So now coming to the table. So with a particular proportional controller gain, whatever be the, say for example, set the proportional gain at 0.6 and all that. So you have to make the appropriate settings in the PID unit as per what I have told you how to do it. Now, in the table, you find that the tacho generator voltage has to be noted, and then N, that's the speed, is going to be given by Vt by Kt. Kt you would note is given in your previous page of the instruction sheet, that Kt value is already supplied. So, and you will be able to get from there. Now, you have to note something which is known as the error voltage. So, error voltage, from where are you going to get that? The output of your op-amp unit is actually the error, isn't it? Because if you would have drawn a block diagram, you would have put the error detector over here, and the output side, you would have got the error signal. So that is the error voltage that is being referred to. So that also, you have this voltage over here, you would also have to note. Now, in fact, while making the connections, so we had not shown the PID controller unit, we showed you how to measure the voltage at this point, isn't it? In the video that was done by a similar thing. Similar process, by using a multimeter, you can measure the error voltage as well. So now, I mean, the other things have to be calculated. Okay, so I'll just take this to the full screen mode, though it is more or less nothing much to it's handwritten, but I hope you can see the slide. If not, let me know. It's being shown in the full screen mode. I guess you can see it because I've shared my whole screen. So now there are, two parts of this table. The first part is, you can see equal to 1. Equal to 1 means actually it's Kp equal to 1. Meaning if the proportional controller gain is set to 0.1, not 1, sorry, it's 0.1. When Kp equal to 0.1, by changing the break position for 2, 4, 6, 8 and 10, you note the readings and put the values in this table. So this has already been done, since unfortunately we are not going to be able to do the experiment. This has been done by some previous batch student, and I will give you this portion of the experimental data from which you would have to do the rest of the calculations and complete your report. Similarly, the next part of the table, this one, is for Kp equal to 0.2. So as I told you, by changing the proportional controller gain, you would have to take readings. So this portion, that is run 1, is done in the open loop. So till so far, basically all the readings that you see over here have to be noted by not connecting the feedback path. So that is the first portion. Tabulation has been already provided to you. The next run, that is run 2, is actually for the closed loop configuration. So for closed loop configuration, basically Kp equal to 0.2, notings have been done. Kp equal to 0.6, the notings have been done with different break position settings, of course. And sorry, there's a typo over here. In the heading, I've copy pasted and written open loop. It's not open loop. This is in the closed loop. I'll just change it. Sorry. It's written over here. Closed loop is written. Forgot to change it. It was a typo actually. I had overlooked. So run 2 is for the closed loop configuration. Closed loop means the tacho generator output is going to be connected to the input of the summing amplifier. And now for different Kp settings, that is proportional controller settings, and by changing the break position, we are going to make the notings over here, right? Similarly, for a different Kp value, Kp equal to 0.6, again, by changing the break positions, the notings have been done. In the third portion of this table, you find that, though this has been folded, but anyway, I'll tell you, Kp equal to 0.2, Pi equal to 0.1. So this is, the third portion is for the Pi controller. Actually, the readings have been taken, right? So now from these readings, you would have to complete the rest of the report. Now, one thing I would have to point out over here before going to what you are expected to do is that the error voltages have been noted. We find that for Kp equal to 0.2, say for break position 2, the error voltage you note is 0.28, right? For the same break position, if the proportional controller gain is increased, we find that the error voltage from 0.28, now it becomes 0.1 for the same break position, By increasing the proportional controller gain, you would have studied that somewhere in your process instrumentation and control, that as well as in the control systems, linear control system class that we do in the third year, that when the proportional controller gain is increased, the steady state error would be decreasing. So we find over here that actually the error voltage, the value of the error voltage for the same gain setting, for the same break position setting, but for an increased proportional controller gain value, because of the increase in the proportional controller gain, the value of the error is changing. It is decreasing. Similarly, for another, say, break position 8, we find here for Kp equal to 0.2, it is 0.53, whereas for 0.6, it is 0.21. So you see that the error voltage would be decreasing, corresponding to the same break position, of course, if the proportional controller gain is increased. Also, Here we have the P controller in with two values. Now the third reading that is taken over here is for the PI controller. We have also studied in our previous year, that is third years, that when an integral controller is included, meaning instead of P controller, if you have a PI controller, the state error decreases drastically, and which is what we would be noting here as well. So say for example, for break setting of 2, the value was equal to 0.1 for the P controller. For a PI controller, it is 0.01. Similarly, over here, I mean, for break setting equal to 4, we find again it's decreased. Here, of course, I mean, you see that this appears to have the same value for all break settings, and because it is very small, maybe, I mean, there's a slight change in the third position or fourth place, I mean, after decibels, but experimentally it's not possible to note that. It has not been noted. Nevertheless, corresponding to each break position, we find that the error voltage has decreased. That is a finding that, I mean, is noted to be true as well as far as our experimental data is concerned. So that actually brings us to the end of this experimental data sheet, and now I'll tell you, okay, so what exactly will be sent to you and what exactly you will be expected to do. So as I mean has been decided for this semester, I will be sending you one sheet, a handwritten sheet consisting of the experimental data that you just saw on the screen. So I mean both those are there on one sheet of the lab report of one particular student in the previous years. I'll send you actually I think it's a JPG. It would have been better if I could have scanned it, but unfortunately it has not been done. So anyway, it's visible. I mean, whatever values are there, you can more or less make out it visible and understandable as well. So you would first of all, the point number 1 of the report is saying tabulate the results. So you would have to copy the table by table rather, right? Next, give appropriate diagrams as noted. So appropriate diagrams would indicate the block diagram, which is also provided in your instruction sheet, right? The second one is that second step of the report asks you to, excuse me, draw the signal flow graph of the closed loop system. So this has to be done by you as part of the report, right? So this has to be done. The third one says compare the value of the tacho constant, EMF constant, of motor brake constant, all those you would be, I mean, able to see that's there in your instruction sheet. And I mean, you would have to calculate as well and then compare with the instruction sheet and then show your sort of show your comparison. Also, the last one is to, the last portion of the report is to plot the speed torque characteristics of the open loop and closed loop system. So you would have to take graph papers, those two graph papers, one which is going to give you the speed torque characteristic in the open loop, and the next one which is going to give you the speed torque characteristic in the closed loop. So basically what you have to do is you would have to calculate the torque first naturally and then plot it versus speed. Sorry. Does anybody have any idea how to calculate the torque? We have noted the speed. You have the speed available to you as well as other things, other notings that you have seen on the previous slide. How would you calculate the torque? That is my question. You find that also over here in this, there are some typos, 1 and 7 extra. Those writings are extra, but nevertheless, the other things you can make out. So basically, you find that the motor torque constant is actually provided to you, and the unit you can see over here. So from there, that is the hint. Can anybody tell me how you would be able to calculate the motor torque? Any idea? you find this is your torque constant is a Newton meter per ampere. Value is given 10 to the power minus 3 that you can make out. There are some typos, as I told you. In fact, the servo amplifier gain also is volt per volt, meaning it's unitless. There's a typo over there. But anyway, coming back to the torque, how would you be able to calculate the torque on the basis of the data that you have noted?
Motor torque constant into motor current.
Right, very good. So basically, since the torque constant is given in Newton meter per ampere, so from the motor current, if you, just multiply it by the torque constant, you are going to get the motor torque. So that now has to be plotted versus speed, and you would be able to complete the rest of it. So that actually brings us to the end of this presentation, as well as to the end of this class. I will, as I told you, I will send you one sheet which has the experimental data by tomorrow evening latest, and you would have to complete the rest of the report, as well as, of course, do the usual things, meaning there should be a sheet with the title of the experiment, objective of the experiment. All those are there in your instruction sheet, just you have to copy. But you sort of just to get you into the mood of completing a report, which you would have otherwise done while visiting the lab. The report has to be completed. So first of all, the title and the objective, then the block diagram. And then, of course, you would not be able to compile a sheet of the instruments. That is not going to be done because you don't have it available with you. So that we will not be having. Then next would be the experimental data that you already received from me. You have to just copy on a sheet. The next thing would be, of course, completing the report, meaning you have to go through those 1, 2, 3, 4. I think there are 4 of those. Finally, the graph has to be plotted. So when you finish with that, you would have to make a PDF of that and then send it back to me via email to the mail ID from which this link was generated. That is smita.sadhukosh@jadavpur So you need not note it down. You, if you go to the link that was generated, if you go to that mail or whatever you've received, you will find that mail ID over there anyway. So that you would have to send to me by, say, when would it be? By 4th October, I think would be a Monday, if I'm not mistaken. So evening or night of 4th October, I'll give you for completing this report and sending by mail to me, right? So that actually completes whatever I had to say. I'll go back to before going back, I'll stop the recording first. Recording, isn't it? Just a moment, I'll stop the recording. Stop sharing. Okay, stop sharing. And stop recording. Okay. So now, if there is anybody who has not responded to their roles, have not given me your roll numbers in spite of being present, you can let me know now. One by one.
Ma'am, 1180.
Which is your, what is your elective, first of all? Sorry. What's your elective? Who's that now?
Hello, ma'am.
Yes, yes.
Ma'am, my elective subject high voltage.
High voltage, okay. So high voltage, okay. What's your name or roll number, whichever you prefer?
Ma'am, my name is Pooja Datta.
Pooja Datta, okay, I have marked it. Fine.
And roll number 1180.
Okay, 1 is sufficient. Pooja, I have marked you. Anybody else who has not yet responded or has not told me that you are present? Anybody else? Okay, let me just quickly go through the sheet once more. Okay, Shobuj Mondal, I think, is not in this class. Shomodip Bosha, are you present? Shovik Mondal, no, because later on it creates a lot of problems if somebody comes and says they were present and couldn't respond. Ankesh Kumar, Victor Mondal, Supratik Ghoshal, slightly sectional, but anyway. Mm, no, whatever. Educate. Protul Boydya. Protul, are you present? Somebody's coming in. Okay, so and that completes my list. Anybody who has, yeah, Shomodip, you just joined. Have you given your attendance?
No, madam. 1132.
What is your elective?
1132.
What is your elective? I have the roll sheet according to the elective.
Instrument.
Instrument. Okay, just a moment. And now tell me you are Shomodip, na? Shomodip.
Yes. 1132.
1132. Acha. Shomodip, I've marked you. Anyone else? I saw somebody writing on the chat box. Who was it? Faizan, Ahmed Faizan, I think I marked you already, isn't it? What's your elective? Faizan, your elective কি কেউ একটা বলতে পারো? Faizan, what is your elective? If I want to trace you, I would have to first know that. Acha, Faizan Ahmed, I found it. So you told me elective is instrument illumination. Okay. Faizan, you have already been marked. Okay, Protul Boydya turns up now. Protul, what happened? You're joining now, or have you heard what has been said in the class?
No, ma'am. I was outside.
Then
I was
what
out of town. That's why so much network
out
problem.
town means what? This network is available worldwide. Which town were you in? On the moon or Mars?
Right now I'm in Asansol actually.
Whatever, Asansol, you have your mobile with you. Anyway, I've marked you just to sort of make matters easier for me. Because otherwise, again, you will keep on telling me that. Anyway, so Protul has been marked present.
Okay, ma'am. Thank you.
Okay. Anyone else, or otherwise we wind up now. That's all. Thank you. Okay, so I'll leave now.